are you supposed to be?
Your new interns. Software and hardware.
No, I don't care. I need you three to do this for me. 2 words. Imaging, market, disruption. This is the future of the camera. Imagine a way that a picture can be focused at an instant. That's the kind of innovation we do here at Bappel.
Isn't that just called autofocus?
We'll call it Autofocus. Your job is a way to make this dream a reality. The iPhone Y will release in 4 months at the next Bappel convention. Make it happen.
Why do I need to rebuild autofocus? Isn't this already a thing?
Well, there could be other applications for autofocus algorithms, like making cameras faster or more accurate. Or you could put universal autofocus to a new platform like microscopes. You can also validate that your autofocus is correct if you approximate with numerical methods.
Oh, okay. I don't even know where to start.
The big boss man did email us instructions. You should probably start there.
Good morning, losers.
Time to get started on your assignment. As you know, photography changes human lives. This means we need a good way to produce high-quality photographs. There are 2 well-known methods for achieving autofocus, one detecting phase changes in split light beams, and another using a bunch of photo data and comparing edge contrast in pixels. I don't know what that means, but it sounds hard. Your objective is to find a new way to make autofocus happen and make it better. Peace out. I already forgot your names.
Okay, so I found this research paper claiming that we can graph sharpness of images with respect to the focusing distance. It looks like this sharpness function basically takes the shape of a Gaussian distribution.
Okay, but we need a lot of sample data for Gaussian distribution.
But the thing is, we don't need to find the full curve. We only need to find the maximum sharpness to get the optimal focusing distance. So, we can approximate the curve using a technique like quadratic splines.
Okay, yeah, that sounds good. Let's propose this to the boss.
Get in.
We found this research paper that proves that we can use numerical methods to approximate the optimal focus distance. Allow me to explain. The algorithm gathers a set of image data from which we can determine the focus distances and as well calculate the sharpness values. So when we calculate each sharpness value for the images, we can plot the data on a 2D Cartesian plane with the focus distances on the x-axis and the sharpnesses on the y-axis, from which we can attempt to fit a curve to the data. We will use the method of quadratic splines to approximate the curve and then find the optimum, which means we can determine the focus distance required for the autofocusing algorithm. Are there any questions?
No, that was garbage. You're fired. Get out. You. Do you have any ideas?
We can use cubic splines instead of quadratic.
I like it. Raise. Get started on it immediately.
I think we should start with defining our inputs and our outputs. So our inputs to the algorithm will be a set of images for a single test subject, taking out a variety of different focus distances, and the hardware intern is going to do that for us. And using this data, we need to output the optimal focus distance for the camera in order to take a sharp in-focus image.
But how can we do that?
Oh, here, it'll be easier to explain this way. Images can be loaded as a matrix indexed by x and y coordinates, where each element represents the intensity of the pixel at a given xy position. From this, we can calculate the derivative of an image.
You can take derivatives of images?
Yeah, they're just changes in intensity in a given direction. Like take this image matrix, for example. The derivative is defined by a weighted sum of neighboring elements. So, if we wanted to calculate the derivative at this point, well then this would be the result.
Okay, but then how do we get the sharpness from that?
Well, you would know if you did your research, idiot. Focus images have clearly defined boundaries, which creates a big change in intensity, and blurry images would have gradual changes in intensity, which would yield lower derivative values overall.
Oh, that makes sense. Then we can take norm of the matrix to get the sharpness value.
Yeah, that's right. In most research papers, they take the Frobenius norm. A sharper image will have a larger Frobenius norm for the image derivative, and we do this for all the images in the dataset, so we can get data points in the form of focus distance, sharpness value.
Cool. So are we done?
What? No, not even close. We need to fit a curve to this data. Now, according to our research, the true curve would be a probability density function for a Gaussian distribution. But for us to fit this curve to the data, we need a very large sample size. So instead, we're going to use the technique of cubic splines. Given a set of data, we approximate a smooth curve using piecewise cubic functions, where the first and second derivatives are continuous at the data points, and the second derivative at the endpoints are equal to 0. Since the xy coordinates of all data points are known, the coefficients a, b, c, and d must be solved for. We can set up a linear system of equations to be solved using any matrix solver, like Gaussian elimination. Solving gives us everything we need to define the approximated curve, and now we just need to find the maximum.
We only know how to find roots of an equation, but what about optimums?
There's a method called the golden section method, which can find local maximums on a bounded interval by iteratively narrowing down the search interval. Now let's say we have a curve bounded by x low and x up. The golden ratio, which is approximately 0.61803398.
How do you remember all these digits?
It's not that hard, it's just, I've only written 11 digits, really. Anyway, using this ratio, we can define two more points, x1 and x2, which are offset by a distance d from x up and x low, based on the golden ratio. If x1 is greater than x2, then we know a local maximum must exist here, so we can narrow the search interval for this. We can change our search bounds and keep repeating until satisfied with the error.
That was a lot to take in.
Yeah. You think you can code it?
I'll try. Let's get to work.
Thank you. Okay, you can shut up now. As you all know, here at Babel, we strive for innovation. Tonight, I'm proud to present an original, groundbreaking concept that I, Big Boss Man, have developed by myself.
What does he mean, developed by himself? We did all the work. I swear, I'm gonna...
And now, ladies and gentlemen, I present to you, Autofocus. So what is autofocus? There are two well-known types of autofocus on the market.
He took our slides too? This is a Policy 71.
Here's how the algorithm works. Let's say you want to take a picture with your Babel iPhone. The algorithm will collect a set of images at different focus distances. Oh, hey, those are the photos I took. Here's an example of photos that I took. Oh. These photos are sorted by increasing focus distance. Our algorithm finds a focus distance that provides the maximum sharpness. Damn right you do. After doing some calculations, we can plot relative sharpness with respect to focus distance. Here are some of our results. Each of these graphs represents the sharpness function for a different dataset. Shown here are the results of 5 datasets of 14 images each. The red line connects the data points from which we fit the black cubic spline and calculate the optimum. We compared our results with the true value of focus distance for each dataset, which we measured with a ruler, revealing an average error of 8.51%. That seems low to me.
Is that low?
Yeah, it's reasonable. There was a lot of chance for error. We had non-linearly distributed focus distances and accuracy error resulting from approximating the Gaussian distribution with cubics. We would have gotten better results by collecting more data to better approximate the curve, but that wouldn't have been practical in terms of computation time.
Shh! I can't hear Big Boss Man. I want you to understand just how much work I put in to make this happen. Iterations upon iterations of unused methods. I started with quadratic interpolation, approximating the function as a parabola. However, this method required data points to be evenly distributed about the optimum, which wasn't realistic. One of my interns even suggested quadratic splines, but everyone knows it's inferior to cubic splines in terms of stability and accuracy. But, thanks to my expertise, we decided smartly to collect data points at evenly spaced focus distances, reducing the chances of the cubic spline overshooting the optimum. Autofocus will be available for purchase on iOS 11. Thank you.